Okay, let's do a quick refresher on matrix multiplication for those who have seen it before, and a quick introduction to why we multiply matrices the way we do, and that's to get consistent answers based on the equations the linear transformation equations that we're dealing with. Okay, so just as a reminder from the previous video, matrix multiplication involves multiplying rows by columns. Okay, that's important to realize. Okay, let's as a slow introduction to this, let's just take 3 transformations that we've dealt with before and try and figure out what the transformation matrix is for each of these. Okay, well, if you remember, the reflection in the x-axis involved this transformation where the new x is the same as the old x, but the new y is the same as the negative of the original y. Okay, and the same for reflection of y and reflection through the origin. These were our transformation equations. Okay, let's take the general case and use that to figure out what the transformation matrix is for these transformations. So here we would have x dash y dash equals our transformation matrix times x, y. Okay, this is always the matrix equation that we have. The new vector pointing to the new position is the transformation matrix times the old position. Okay, good. So, seeing as this should be a, b, c, d, but here are our equations here. So, if x dash is equal to x, that means a is 1, and b is 0. Okay, and y dash goes to minus y, so c is 0 and d is minus 1. Okay, so let's see if that multiplies out to give back. I'll just do one example, the x dash equals x. Okay, so we're going to multiply rows by columns. So we're going to multiply this row times this column. Okay, so x dash is equal to 1 times x plus 0 times y, which is equal to x. So that works. Okay, and you can go down and do the same for the y dash and figure out that you must get the same equations back here through our row times column matrix multiplication process. Okay, good. Let's figure out what the matrix transformation is for this one. Good, so x dash is equal to minus x. So a here must be 1. There's no y component, so that's 0. Y dash equals y, so there's no x component, so that's 0. And this should be y is 1. That should be minus 1, I'm sorry. That should be minus 1. You need to get back minus x. Okay, that's the matrix equation representing this same linear system. And then this one here is x dash y dash equals the transformation matrix times x, y. Okay, x dash goes to minus x, so that's minus 1. There's no y component, so that's 0. Y dash equals minus y, so there's no x component, but there is a minus there. Okay, this is all, remember, comparing back with our original set of equations here. And this transformation matrix always being a, b, c, d, the coefficients in red. Okay, now once again you can verify all this. You can do row by column multiplication to see that you get back these original equations. Okay, so this was matrix vector multiplication, or in other words, we were always multiplying a 2 by 2 matrix times a 2 by 1 matrix. Okay, I should say that it is a general rule that if you're multiplying two matrices together, the number here and here ought to be the same. Okay, and the result is the two outside numbers. So the resulting vector we get when we multiply a 2 by 2 by a 2 by 1 is a 2 by 1. Okay, the reason these numbers need to be the same is you need to have the same number of rows as columns in order to do the row by column multiplication. Okay, but the question remains, how do you do more general matrix multiplication? Let's say you have a 2 by 2 matrix times a 2 by 2 matrix. Okay, let's do that here. So what I'm going to do is I'm going to take this this matrix here, minus 1, 0, 0, 1, and I'm going to multiply it by this one here. So minus 1, 0, 0, minus 1. Okay, and we're going to figure out what we get. Well, first of all, you have to ask yourself, can this be done? Okay, this is a 2 by 2 times a 2 by 2. Okay, it can be done because there's the same number of columns as rows. Okay, and the product, the result, is a 2 by 2. So we expect to get a 2 by 2. Okay. What you do is you do the same thing. You go rows by columns. So you take this row first and you multiply it by these two columns. So the first row times the first column gives you minus 1 times minus 1 is 1, plus 0 is nothing. Okay, so 1 is our first number in the multiplied matrix. The next step is to take this same column or the same row and multiply by the second column, and that will give you the number here. So minus 1 times 0 is 0, and 0 times minus 1 is 0, so that number is 0. Okay, that's taking this first row and multiplying by the second column. Now for this number down here, we're going to take our second row and multiply by the first column. So we get 0 times minus 1 is 0, plus 1 times 0 is 0. So that's 0 also. And then the last number here is going to be the second row times the second column. So it'll be 0 times 0, which is 0, plus 1 times minus 1, which is minus 1. Okay? It was clear in the beginning, I hope, that when you multiply a transformation matrix by a vector, you get out another vector, because that's the process. You're moving or transforming one point to another point in the plane. What does it mean to multiply a transformation matrix by another transformation matrix? Well, this is the amazing bit. Multiplying one transformation by one transformation matrix times another is the same as doing this transformation and then doing that transformation. Okay, so here's the clever bit. Look at the matrix we got as a result of doing this and then this. Okay, these two that we chose were the reflection in y and the reflection in x. Sorry, the reflection in y and the reflection in the origin. Okay, but the reflection in y times reflection in the origin. Okay, actually in this case it's the reflection in the origin. Yes, that's correct. Doing the reflection in the origin and then doing the reflection in y. Okay, that's not visible. Doing the reflection, this one here is reflection in the origin transformation, and this one is reflection in the y. Okay, doing those two combined, well, we got the same as this transformation matrix here. So what that's telling us is that combining a reflection in the y-axis with a reflection in the origin is the same as doing a reflection in the x. Okay, which is exactly right. Okay, if you think about it, if you look back at the previous videos, if you reflect a point in the, if you take any point here and reflect it in the origin and then reflect it in the y-axis, it's the same as having reflected it in the x-axis to begin with. Okay, so that's why writing our linear transformations in terms of vectors and matrices is a really powerful way of doing things.